Thank you for the introduction. It's a real pleasure to come to this city with a rich history and to talk about our work at FM Global on the suppression physics for sprinkler protection. Before I start the talk, I would like to acknowledge my co-authors, Yap, Carl, Xiangyang, Sai, and Bert. They're all from FM Global. We have a group of people collaborating in this area to try to develop a new tool to give us the predictive capability, just like Ron Albert discussed a few minutes ago, that allow us to actually predict what's going to happen for sprinkler fire. This is an overview of my talk. First, I would like to introduce the sprinkler technology, the pros and cons in the practice, some of the effectiveness in the real industry applications. And then I will describe talk about the motivations that we have. Why do we have to develop a numerical predictive capability for sprinkler technology? The approach that we're taking is a combination of experimental technique and numerical methods. I will describe the numerical model in a very short time because my work with this is pretty much focused on the experimental side. So I will spend most of the time talking about the exploratory study for the key phenomena and the physics associated with them. I will summarize the work that we have done so far and show you some of the ongoing work we're still doing at FM Global. First of all, many of you know FM Global. For those not familiar with us, we are one of the largest commercial property insurers in the world. We have about 1/3 of the market in North America, about 1/4 of the market in the world. So our experience is sort of representative of the application of sprinkler in the industry and commercial buildings. No matter where you go, in the North America, in Europe, or all over the world, you see if you put sprinkler into the building, the protection, the effectiveness of the sprinkler protection is dramatic. It makes a huge difference. So with that, FM Global spent many years. I think Ron mentioned that started actually in 1950s, if I remember that correctly. For 1.5 century, we do continuous research in this area. But in the new millennium, that we actually ran into troubles. The trouble comes from two different ways. One is that we ran into the limitation of our testing capabilities. Some modern facilities, they can build the storage all the way up to 100 feet tall. And our test facility, which is one of the largest in the world, is only 60 feet tall. So we basically run out of space. That's one thing. It's hard to imagine you build higher and higher buildings for that purpose, to do one-to-one ratio industry testing. The second issue is a little bit more troublesome for us because it actually comes from the effectiveness of sprinkler system. People start to use them more and more. And every time you use a sprinkler for a particular building, people ask you specific questions of that building, that fire scenario. For instance, if you test a rack storage with all these standard boxes in place, and they ask you, what if I have those boxes missing in my storage? Is it going to be worse, or is it going to be better with the same protection you tested? And same thing that our standard test says that, okay, we always use about a 6-inch flue space, which is about 15 centimeters between those storage boxes. And then the real engineers in the field will say, okay, what if I have a box missing, and also I have this flue space all over the place? Some of them may be a couple inches, some of them may be like this wide. What do you say about a sprinkler protection? Is it going to be better or worse? There's a lot of variations from the standard industry test that you can do, and the question is, how do you generalize the results that you have to different scenarios for fire hazards? So the large-scale testing is very expensive. This is a picture of a full-scale testing. I think this storage is probably 6-7 feet high, which is 30-35 feet high in terms of the storage. And you have a sprinkler activation. and you can actually measure from global quantities to determine whether or not the sprinkler is effective. But for this kind of test, one particular test typically costs anywhere from $10,000 to $100,000 easily. And the test is only 50 minutes, but it takes weeks to prepare sometimes. So the cost is so high that it's just not practical to do this for every single fire scenario. What do we do now? Well, one immediate answer to this question is you go to a smaller module of your test array, and you test it from there. The challenge here is that the smaller array, yes, you can create a smaller array, but from the point of view of science, that you actually need to do a rigorous scale model. You scale down everything. You have a smaller sprinkler, you need to have a smaller commodity. But that is, very often, that's not practical. I mean, where are you going to find that smaller commodity and smaller sprinkler? You can't design new things and manufacture them, and that becomes a very, very costly. So what we do is we actually take smaller fuel array and run this kind of suppression test to apply uniform water flux on top of it. We try to measure the response characteristics of those different fuels in different scenarios and compare them, and we call this particular method commodity classification. It's not as rigorous as a scale modeling can do, but it gives you a little bit of rough answer, so you can put different commodity into the bigger bins, and you assign a representative protection for each bin. That's how you do it. So some of the problem can be addressed by this kind of approach. But there are many more problems you cannot solve with this kind of approach. What you can do is that you rely on numerical modeling. Hopefully you can do parametric study to generalize result with a limited full-scale test and experiments. That's what we're trying to do at FM Global. Before you can develop any numerical model, there are two things you have to know. One is what is the key phenomena, and the second, what are the physics? What are the equations that you can use to describe those physics? So the key phenomena is shown in this picture. Actually, I think Ron just did a wonderful introduction for all the key physics in sprinkler suppression. First of all, you have to know what's going on around the sprinkler. In other words, you have to know the spray formation and the initial condition of those water spray. We find out the end result that the delivered water on top of the fuel is very sensitive to the initial property that you assign to the sprinkler spray. So you have to know this. And then for many, many sprinklers open on the ceiling, you have to know the sealing flow and the interaction of the sealing flow with the droplets. When you go down this trajectory of the spray, you realize that you need to understand the interaction of spray and fire fluid. And then if you go further down, now you have the water on top of the solid commodities you need to protect. Then you need to know detailed physics and phenomena in this area. For instance, how does the water move? What is the transport of water on those commodities? And what is the interaction between the water, the fire, and the solid fuel? So you have multi-phase interaction going on for this part of the problem. So you can see it's quite a complex problem, dynamic, three-dimensional, and it's a multi-phase phenomenon. This is a huge problem for us. So we decided, in order to have a reasonable description of all the key physics, we need to come up with a basic framework for our model. The model we're developing right now is called fire foam. The four-letter FOAM has nothing to do with the foam that you put out the liquid fire. It's actually abbreviation of field operation and manipulation. It's based on the platform called OpenFOAM, developed here in the UK. It's open source code. We basically have a module to deal with the gas phase, momentum, mass balance, species transport, energy equation, and you have ideal gas law here to simulate the gas phase. For the solid phase, we have the heat transfer equation and the pyrolysis, basically the chemical decomposition of the solid fuel into gas. Now, for the liquid part, it's actually a little bit tricky, because if you look at the water, and most time we're talking about liquid, is water for sprinkler protection. you have the droplets that Ron just described. You need to be able to calculate the trajectory of those droplets and make sure that you get the right amount of delivered water on top of the fuel. Now, that can be taken care of by the transport of the droplets in gas phase using a Lagrangian transport scheme. For the water transport on solid, actually you have the water flow on the boxes. We developed another module using O'Leary's scheme to simulate the flow on the box surface. As many of you know, that we actually have a good knowledge of the gas phase. I mean, you know the fundamental equations, mass balance, species, momentum, all of that. People have been doing this many, many years in the fluid dynamics and the combustion area. For solid heat transfer, it's not a big challenge for us either. But pyrolysis has some issues and you have to deal with. The basic challenge comes from the measurement of materials properties. How do you measure what are the material properties you need to quantify to give you the input so you have a reasonable simulation of the pyrolysis? The real challenge comes from this side. We know the Lagrangian transporter can help us to understand the interaction of the droplet and the spray transport in the fluid, in the gas phase. But we have very limited knowledge on this particular part, which is what is the way that water flows on the solid surface. How does that interact with the gas phase, which is basically fire, imposed heat flux on the surface? And how does that protection actually happens for sprinkler applications? So we spent a lot of time to figure out this part. And that will be actually the focus of my talk today. This is some of the illustrations that we used for the water transport model. Because of the thickness of the water flow, which is most of the time looks like a film, sometimes it looks like a rivulets, but no matter which case, the thickness of that film is so small compared to the tangential direction, any dimensions in the tangential direction, either the width of the rivulets or the whole boxes. So we decided that it's reasonable to simulate the transport of water using a so-called thin film assumption. Basically, you have transport in the two tangential direction on the surface, but in the normal direction, you do all the balance, but the velocity assumes to be zero. There are a lot of phenomena going on the film surface. You can have droplet impinging on the surface. You can have splashing of water. You can have evaporation of the water because of heating. You can actually have boiling in some cases. You can have film separation from this. For instance, you have box. When the water goes to the corner of the box, you start to have separation. And the film interacts with the solid behind the water film. And you have heat transfer, you have mass absorption. The porous material like corrugated cardboard can absorb water. And you have the shear stress that limited the transport velocity of the film. So we developed a basic transport model to describe all this phenomena. Now, the key question is, what do you do with all this phenomena? For most of the fire engineers, we have very, very limited knowledge in those phenomena. So we decided to start a research program in FM Global to basically look at the subcomponent of each of those phenomena. The first thing we realize is that if you, it's widely used in all kinds of industries to put stuff in the corrugated cardboard, paperboard, and the paperboard absorbs water. So we look at the water absorption, see if that's the controlling phenomena to stop fire propagation. What we did is we actually measured absorption of water on top of the corrugated cardboard, and it looks like it scales as 1/2 power of the time versus the cumulative absorption per unit square, per unit area on the field surface. But we also realized a significant impact of the water temperature, because once the water penetrates through the fire, it will not stay at 20 degrees C. It will be some elevated temperature. We also look at some theoretical estimation of whether or not the change of the surface tension or viscosity of the water can take care of this kind of significant change in terms of absorption. But actually, there's a quite large difference. So we're still working on this part, trying to figure out why this happens for the water absorption. But from the result that we have, the water absorption accounts for, if you take the overall input flow, the amount of water being absorbed is actually quite a small fraction, usually less than 5%. So the absorption does not take the significant the most of the energy that needed from the fire to evaporate the surface flow. So what happens is actually the vertical flow on the surface. This is actually a high-speed camera photo for the water flow on a stainless steel surface. The stainless steel is polished. We have a heat flux gauge here in flush with the surface to measure the heat flux behind the water film. And then you can see the structure of the water film. It's not that smooth. It's a lot of detailed structures. So what we did is we used a technique called laser reflection-based technique to try to measure the thickness. And if we have two probes with a fixed distance, we can figure out the transport velocity in the vertical direction based upon the correlation of the film thickness. So the result that we see from this kind of measurement shows that if you compare the vertical surface velocity of the water flow on a fuel surface, actually it agrees quite well with the classical solution by Nussel, published in 1916. So we can assume that Nussel basically assumes it's a laminar flow on the vertical surface. So if you can take care of the vertical surface flow of the water, assuming it's a laminar flow, you get a reasonable simulation on that part. That's what we use right now in our code. But like I said before, when you have the water flow reach the bottom of a commodity or a box, you start to have the flow separation. The separation phenomena is controlled by the force ratio. Basically, you have the gravity and inertia to push the water go straight down, but you have surface tension to drag the flow in the horizontal direction. The ratio of those two gives you some indication how the water going to flow right at the corner. As you see, with a very low Reynolds number, which is basically nothing but the vertical flow rate normalized by the viscosity, you have pretty much all the water going in the horizontal direction. Eventually, the surface friction will slow down the flow, and then will just stream down to the next tier. But if you have a high flow rate, you start to have a separation. You also have a portion of flow going in this direction, quite a bit into the horizontal surface at the bottom of the box. And the angle of this separation has a lot to do with the curvature at the corner. So we developed some empirical model to take care of this part. Now, we know the absorption of water by the fuel. We know the flow phenomena on the surface. We know how they separate the corner. We want to put them all together to look at the transport of water in the rack storage. We're simulating the rack storage by using a rack and the boxes put on top of the rack. We put water collector below those boxes to collect water on the vertical surface to see whether or not our model can simulate reasonably well of the transport by including all the sub-models. And we're working on this, still working on this, but the physics that you can see is that I believe that for panel A is a 0.1 gallon per minute per square foot for water flux. This is probably 0.3, this is 0.6. One interesting phenomenon is as you increase the water flux, you see the wetted area increases significantly. And that tells us, because most of the water flows on the surface as a runoff water, not being absorbed by the commodity. So actually, the wetted surface area is probably a controlling factor of the fire propagation. In other words, if you have a whole area covered by a film flow, if you do the potential, the latent heat of the water multiplied by the flow rate, you estimate how much energy you need actually to get rid of this water. And it's a very, very significant amount of heat flux you need. So if you can have water fill the cover portion of the boxes, you probably have this box well protected. Otherwise, for this case, you have a lot of surface area exposed to the fire. You probably can have the fire propagating across this surface. So that's what we find out in the. That's what we see in our experiment. Now, all the experiments I talk about so far are basically cold flow experiments. They take care of the transport part of the water flow. In order to reach the final stage that we can predict what happened between the fire and the water and the commodity, the solid fuel, we need to go more complicated phenomena. We need to look at a more complicated phenomena than the cold flow. What we do is by design experiments in the increasing complexity to tackle this problem. One level more complicated than the cold flow is actually we set up a vertical panel to apply the water on the surface of the panel. And then we simulate the fire using a radiant panel on one side. Now you have the fire heat flux simulated as a radiant panel. It's a constant heat flux. And we want to look at different water flow on the surface so that we can see what is the rate of evaporation created by this heat input from the radiant panel, and what is the burning phenomena if we actually have a fuel surface instead of an inert surface. One interesting phenomenon that we saw in our experiment is that once you apply the heat flux on the surface, this is a steel panel, you start to see the transition of the flow pattern from film to rivulets. Then we realized that in our model, we have to be able to describe both flow patterns. At the beginning, we think we should be fine by looking at just the film flow, but we realized that once the film flow changed to rivulets, we have to have separate model to deal with the rivulets. So we look at this kind of experiment to help out to understand the evaporation rate, for instance, on a particular surface. This is 41 centimeter by 46 centimeter area exposed to the radiant heat flux. Different radiant heat flux normalized by the water flow times the latent heat of water. And this is the evaporation rate normalized by the inflow condition. And we see that actually all the data collapse quite a while on the single curve. As you have more and more energy input, the evaporation increase. Not exactly linearly, but it's a monotonic increase. So, but again, I want to emphasize this particular result is probably specific to this the test configuration that we used. We don't expect this kind of curve can be generalized by any vertical surface. But anyway, this is a good set of data for us to use to validate the model. To basically evaluate the model whether or not you can calculate the evaporation part with a reasonable accuracy. The suppression is only part of the story. Another part of the story, like I said before, is the transition from film to rivulets. That's controlled by a phenomena called Maragoni effects. Basically, the surface tension increase as you have the temperature gradient across a certain area. We also look at this phenomena. We basically, the experiment that we did is on a vertical surface, we apply the water with a fixed water flow first, then we adjust the distance of the panel until the point where we see the transition from film to rivulets. And that's how you get the critical heat flux that can change the water from film to rivulets. And this is another set of data that can help us to make sure the model have a reasonable simulation between the two different flow patterns. Like I said before, we design all experiments with increasing complexity. Once we go beyond the inert panel, we need to actually put a fuel surface on the panel. We apply the water on top of the surface first, then we have the igniter at the bottom, and then we apply the radiant flux on the other side. And this kind of experiment allows us to look at the burning characteristics subject to the application of water on a single surface. So it's still very, very simple geometry, well-controlled experiment, but it gave us a lot of insight how the fire will propagate subject to a certain amount of water. So this is another set of experiment, more complicated than inert surface flow, but give us good experimental data to validate the model. If we want to go one level in terms of the complexity, we need to look at another geometry called parallel panel. Ron spent some time to talk about this geometry. Basically, two panels. You put fuel on the surface of the panel, and you have a fire source at the bottom. I think Ron's work is focusing on the part which we call free burn. Basically, you just let the fire go. See how fast the fire can propagate on the vertical direction. In our suppression study, we actually apply the water on the two panels first. make sure the water flows down in a steady state with a controlled flow rate. Then we start a fire and see whether or not the fire can propagate to the top of the fuel. We also measure the heat release rate with respect to time for different water flow rate applied on the surface. So we change the free burn parallel panel experiment to a suppression test. It's still very simple geometry, but now you have a much more complicated physics going on. Because from the fire, you have heat transfer to the surface by radiation and convection. For this scale of fire, the heat transfer usually is dominated by radiation. The radiation, we change the flow pattern. Even you apply a film flow on the surface at the beginning, very quickly, the heat flux will change the flow pattern from film to rivulets. And the interaction of the fire and the water flow and the fuel behind the water is what we're interested in. So you have three component coupling here, and this is a very, very strong test for our model to see whether or not a model can handle the interaction of different phases. But we still test it in a rather simple geometry, which is nothing but two parallel panels. So at this point, if our model can successfully predict this kind of behavior, we feel that we have enough physics in our model to help us to capture all the essential processes in sprinkler suppression. So we did, we pretty much finished the exploratory phase of our study, which is basically focusing on evaluation of experimental technique and look at different design of experiments to see what kind of data we can get from those kind of experiments and whether or not they're suitable to validate our model. So that's the exploratory phase of our work. This is some of the data for the parallel panel suppression test. Actually, as you can see, when you increase the amount of water applied on the surface, the accumulated chemical energy over a certain amount of time decrease almost linearly. Another way to look at it is look at the peak heat release value you can achieve in a single test with the different water application rate. And it still follows the same story. It's not linear, but it's still monotonic decrease of the peak heat release rate with different water application rate on the panel. So to summarize the exploratory work we have done so far, especially on the experimental side, we did a lot of work on the experimental side to try to figure out a better way to evaluate sprinkler technology. In order to improve sprinkler technology, we need this tool. The approach we're taking to develop this new tool is to combine both experiments and the numerical models. We have been working in this area for almost 3 years, and we're expecting in probably in a couple of years we should have the first version of our basic model to help us to model the suppression physics of a sprinkler application. The experimental side, we're focusing on study of the key physics of the key phenomena. On the modeling side, we're developing a three-dimensional transient code using parallel calculation to couple the three phases of the sprinkler suppression. The gas phase, which basically take care of the fire, the liquid phase to take care of water droplet, and also the film flow on the surface, and also the solid phase to take care of the heat transfer and the pyrolysis in the film. What we're doing right now is look into some more phenomena that we think is also important in our study. One of the phenomena we didn't look in the past, but we're working on right now, is called splashing. Basically, you have a droplet heated horizontal surface, and you have this splashing. We realize that when you have many, many tiers of commodities stored in a warehouse, for instance, when you apply a certain amount of water on top, actually the water gets lost. Every tier you go down this rack storage. And one of the controlling factor is the splashing. The water splash on the edge of the boxes, and you end up water losing into the flue space. So we look at the splashing phenomena right now. Another thing that we're working on right now is that the single wall suppression and evaporation test that we did in the past is limited by the power that we have in our experimental apparatus. Now we're having a new apparatus called intermediate scale calorimeter. It's basically a very large panel with smaller burners on the panel. And this is, in front of the panel is a water-cooled spring. And you can set up your vertical panel on this side. And when you start your experiment, you basically slide the spring away and you expose your field surface to a radiation. We can achieve radiation on the order of 50 kilowatts per meter square on an effective area about 1 meter square. So this is give us a reasonable scale to simulate actually one module of our box commodity. We're continuing our work in the parallel panel area. We try to come up ways to have more uniform distribution of the water flow on each panel. On the paper, you say, okay, I apply the water on the vertical surface, but in theory and in practice, when you look at those water distribution, it's very, very difficult actually to create a uniform distribution on the two panels. So we're trying to figure out ways to improve that experimental technique. And this is some of the result that we have. As you can see, as you increase the water flow, you get lower and lower heat release rates. And this is the response of the interaction. This is the result of the interaction of the fire, the water flow, and then the pyrolysis of the fuel. So this is a good set of data for us to evaluate our model. Eventually we have to move beyond simple geometry like a parallel panel. This is what we use for a more complicated model evaluation, more complicated fire scenario. We call this rack storage. Basically, you have the boxes. Each box is about 1 meter cube. Inside the box is a metal liner fit with the box. Basically, you want to make sure that the box can't burn through. It's a metal liner inside to prevent that from happening. And we set up this rack storage, and we light the fire in the middle, and we apply the water. Uniform water flux, different water flux we can try apply on top of the fuel array, and we open up the water at different time of the growth curve of this fire, and we can see the suppression phenomenon. If you apply a lot of water, for instance, this is 12 millimeter per minute water flux, you get the fire pretty much suppressed. But if you apply a very little amount of water, for instance, this is 4 millimeter per minute, you get the fire dip a little bit, and eventually it's going to be out of control. And those tests actually is highly repeatable. We basically repeat the test, you get a very, very repeatable curves. And this is a good set of data for us to use for the model validation to this kind of complicated geometry. For this geometry, we're still only evaluating what's happening below the top surface of the box. We need to know what's happening between the box and the sprinkler. That part is called ADD, actual delivered density. It basically, if you have a sprinkler here and you turn on the sprinkler and with a fixed amount of fire, steady state fire, you want to see how many water actually can penetrate through the fire and reach the collection pans at the bottom of the fire. So this is a diagram showing the collection pans, and those dots are the burners. So we have a rain burner to simulate the fire plume, and we collect the water below the fire to get a sense how the water gets penetrated through the fire plume. We also evaluate the temperature rise and the velocity in this fire plume simulator to make sure that actually what we get from the simulator is actually matching what we measured in the rack storage, real rack storage. This is fire plume data at a different elevation about this, the base of the fire. The final evaluation of our suppression model is a real sprinkler test. So we're going to set up commodities under a ceiling, and we're going to start a fire here and actually install sprinkler on the ceiling pipes and to evaluate the model based on this kind of experiment. This kind of experiment has a lot of uncertainty associated with that. Many of the uncertainty comes from the time activation sequence of the sprinkler, because that's something that you just basically you cannot control. It's very difficult to repeat. So we're trying to figure out ways, we're still working on this, trying to figure out ways to measure the global quantity of the fire propagation, not a single point measurement. Even we put a lot of thermocouples and velocity probes in the fuel array, but we try to look at the global quantity to some sense, either integrated or across a certain cross-section, to figure out where the fire is at a certain time and how we're going to use that to validate our numerical model. So this is probably the final experiment that we need to run to evaluate our suppression model. So to summarize our future work, we work on the cold flow transportation, look at the splashing phenomena, rivulets and film flow, and columnar flow, and also flow. One interesting is that we realize when you have a charged surface, the flow is going to be very different than you have a smooth surface. So we have a dedicated project to look into that. We also look at the single wall radiation controlled experiment with new capability of higher radiation heat flux that we can apply. The final validation for this numerical code will be the parallel panel geometry, the water application test like this, and the full-scale test like this. So we think if we move along this path with all the experiment designed in a way that we have controlled the phenomena, and then with increasing complexity from one step to the next, we should be able to have a more confidence on our model to simulate fire suppression. In terms of the model development, we have a continued effort to evaluate our model for separate effects, like splashing, like water flow on vertical surface, or single wall experiments. We also have validation on the water application test and the full-scale sprinkler test. At this moment, all the components, the liquid phase, the gas phase, the solid phase, are coupled. And we did some very, very preliminary study of our numerical code, and we actually see qualitatively when the fire burns with 8 boxes fire, if we apply a lot of water, the fire is actually out. But if we apply just very little water, the fire keeps burning at a certain burning rate. So this gave us some level of indication that the model is working qualitatively. But there has to be a lot of work that we need to do in the future to make sure that we can get some uncertainty, some sense of confidence level regarding the suppression model. I would like to also acknowledge my colleagues at FM Global, Bob, Sergey, Franco, Chris, Lou, and also Steve Daniello did a lot of experimental design for us, and Dr. Wang helped us understand the model. He developed basic framework in the gas phase for our fire foam model. Many of the experiments we did was actually on the FM Global Research Campus in Rhode Island of United States. Without their staff to support us, the experiment just not possible. So with that, I think I finished my talk, and I'm open to questions.